session lecture. Basically, whoever is there in higher numbers at the beginning is the one that's going to win the competition. Or you can have coexistence. And coexistence doesn't necessarily mean that they have the same exact number, but it means that both are able to persist. Neither one is driven to extinction. Okay, so they'll reach an equilibrium at a non-zero value. So you're going to be able to find, if you're looking at your competition sheet, you'll be able to get all four of those different outcomes. You're going to have, when you turn this in, you're going to have 4 tabs that are on competition and 4 sheets rather, for competition and 4 sheets for predation. We'll get to predation later. But you want to have one sheet that's just your species 1 outcompetes species 2, one sheet that species 2 outcompetes species 1, etc. Okay, and just have those sheets labeled accordingly. Each of your competition sheets will have 2 graphs. Okay, I'll show you why in a second. So, the first thing, just like always, we need to set up our columns. So I'll just put time, species 1, species 2. Okay, if you click this little space in the upper left-hand corner, that highlights everything. And then if you click this middle tab, this is what will put everything in the middle. That just makes it easier for you to see, so I recommend that. So then you're going to want to repeat this. Time, whoops, and 1, and 2. The difference being is that at 0 time, you're going to want to have one run where species 1 starts out with 50, and species 2 starts out with 5, and then in the other run, you want it so that species 1 starts out with only 5, and species 2 starts out with 50. This is so that you can detect that alternate stable state. Okay? If you started both of them at the same initial density, then you wouldn't necessarily find that, you wouldn't be able to detect that alternate stable states, or that situation where either species can win depending on the starting conditions. I'm going to bold this real quick. So then do the time thing just like normal, so equal sign, and just take the previous cell plus 1. There's no defined number of time steps, just drag it out until you can see what the equilibrium point is. Oh. Same thing over here. Okay, so then we're going to have each species is going to have its own carrying capacity, so we'll have K of 1, K of 2. Each species will have its own growth rate, R of 1, R of 2. Okay, and I don't care what you make those, just make sure they're different. So I'm going to make species 1 a carrying capacity of 500, species 2 is going to be 400. Then for intrinsic growth rate, you're going to want to choose a value between 0.5 and 1. That way you get enough growth to see the dynamic, but you don't want to get into those crazy limit cycles or chaos at this point. So I'll just choose 0.7 and 0.8. Then, and here's the key, we need to have our alpha and beta. So remember, alpha is the effect of species 2 on species 1. Beta is the effect of species 1 on species 2. And once you get everything set up, these are the 2 values you're actually going to be playing around with. Okay? There's going to be a swing point. There's going to be a point where below this value you're going to get stability. Above this value is when you get species outcompeting each other, or the alternate stable states. I'm not going to tell you what that value is. You're going to have to experiment a little and kind of discover it. But I'll give you a clue. The intra-specific, you basically, I can't remember how I put this before. The intraspecific competition coefficient is intrinsically in the, is kind of intrinsic to the formula, okay? And so the intraspecific coefficient is going to be about 1. So I'll just give you that clue. It actually is 1, not about 1. So then you have to code this. And so there are instructions on your sheet, but I'll just do it along with you. So you have to take the previous time step times exponent, then species 1's growth rate. You should put a $sign in front of both the column and the row for this. You want to keep this constant. Give a couple parentheses. Then you do your carrying capacity. Add $signs to keep it constant. Then subtract the previous time steps population. And then you subtract the impact of species 2 on species 1, keep that constant, times the number of species 2. And all that is divided by the carrying capacity. So you should keep everything constant except for the population levels, where they appear in the equation. Then you just need to do the same thing for the next one. This time it's R2 because we're dealing with species 2. Carrying capacity is species 2 minus 2.